Hello, this is Robin de Graaf with another video on the basics of in vivo NMR. And today we're going to talk about shaped RF pulses. So in the previous video we talked about the square or hard RF pulse. That's the simplest RF pulse you can have. Basically, you turn it on to a certain amplitude, B1 max, then you leave it on at a constant amplitude, and then after a pulse length t, you turn it back off again. When you look at the magnetization and the spin orientation sphere, you can see that the magnetization before the RF pulse is along the z-axis, m0, and the B1 is perpendicular to m0. Now at this point it is important to remind yourself that the B1 is not a stationary field, but it's a rotating magnetic field. And it rotates at the same frequency as the nuclear spins. So it rotates at or near the Larmor frequency, which for most magnetic fields is in the radio frequency range. So the magnetization and the B1 field are perpendicular to each other. The magnetization experiences a torque from B1 and rotates towards the xy plane over a nutation angle alpha. Now this alpha is proportional to the amplitude of the RF pulse, B1, and the duration of the RF pulse. And you can use either one or both to fine-tune this flip angle to be 90 degree, or let's say you double the amplitude, it will be 180 degree. Also in the previous video we talked about off-resonance effects, because what I showed you in the previous slide, that was for on-resonance spins only. So on-resonance means that the Larmor frequency of those spins and the frequency of the B1 magnetic field are one and the same. So in this picture, the NAA and acetyl aspartate resonance has the same frequency as the applied B1 field. Both are 128 MHz, and in this case NAA is said to be on resonance. On resonance, the magnetization rotates nicely around B1 over a flip angle alpha, as I described in the previous slide. If NAA is on resonance, that means that all the other resonances are automatically off resonance. If we look at the creatine, for example here, the B1 of course is at the same frequency, exactly 128 MHz, but the frequency of this peak is 128 MHz plus 243 Hz. In other words, this peak is 243 Hz off resonance. Now if you look at a picture like this, that basically adds an off resonance vector along the z-axis. Together with the B1 field, that makes up an effective field. And for off resonance spins, the magnetization doesn't rotate around B1, no, they rotate around the effective field. And that has two effects. First of all, the magnetization doesn't rotate, for example, a 90 degree, but a little bit less. And second, the magnetization ends up somewhere in the xy plane. In other words, the phase is not zero. It's not nicely along the y-axis. Now, if we would do a quantitative calculation for all the different frequencies, we come up with a so-called frequency profile of a square RF pulse. This is a 1 millisecond square RF pulse achieving an on-resonance 90 degree flip angle. You can see here, this is the frequency. If the frequency offset is 0, we're on resonance. And on resonance, indeed, we have 100% magnetization along the y-axis, and there is no mx or mz. So that is what you want. But you can see that off resonance, that situation doesn't hold true. My becomes less, mx becomes more, and mz becomes more. So this is now the frequency excitation profile for a square pulse. It is useful for a number of applications, but not for all applications. Some applications, like slice selection in MRI and MRS, require a frequency profile that looks like this, where you have excitation only in a certain frequency band and no excitation at all outside of that frequency band. Now clearly the square pulse is not like that. And so for the remainder of today's video, we're going to talk about methods to design a frequency profile that looks like the green profile, a frequency-selective frequency profile. Now, one of the ways to design that is to use the Fourier transformation. If we look at a square RF pulse again, if we do a Fourier transformation of this time domain signal, we're getting a frequency domain signal that looks like a sinc function. Now, the Fourier transformation is a reversible operation. So if we have an RF pulse that has a sinc modulation, then you would expect it to be a frequency-selective excitation profile, right? One goes with the other. So let's try that. Now, unfortunately, the sinc function is an infinitely long function, so you can never really apply that in reality, so it needs to be truncated. And typically it is truncated at the 3rd or 5th or 7th zero crossing. Again, remember that the sinc only refers to the overall modulation, right? The pulse itself is still applied at the Lamo frequency. Now, this is now our truncated sinc function applied as an RF pulse in the time domain. If we then do a Fourier transformation, then indeed we get a pretty reasonable frequency selective profile where we have excitation here and very little excitation there and there. It may not be perfect, but at least it's a start. Let's look at it in a little bit more detail. Here's again that frequency, the amplitude modulation of that sinc RF pulse. If you now quantitatively calculate the frequency profile, then you can see that indeed it is fairly reasonably frequency selective. There is no inversion there or there, and there is a reasonable inversion there. Clearly, there's also some things that we don't like about this, right? There's areas there and there where we have partial inversion, and there's areas there and there that really don't give good inversion. Now, there's two reasons for this. The first reason is that we had to truncate this RF pulse, which was an infinitely long function. It had to be truncated, and that leads to some of these artifacts. The other reason is that we used the Fourier transformation to design this pulse. Fourier transformation is a linear technique. If you have the Fourier transformation of a signal A, and you have the Fourier transformation of a signal B, and you add those together, that will be exactly the same as calculating the Fourier transformation of A plus B. NMR doesn't work that way. NMR is a nonlinear process. If you have the magnetization after flip angle A plus the magnetization after flip angle B, that is not the same as the magnetization after flip angle A plus B. So if you graphically show this, then the response of the Fourier transformation is the linear line. The response of NMR is a sinusoidal function with the highest amount of mxy, the highest amount of signal, when the flip angle is 90, but that reduces to 0 when the flip angle is 180. With the Fourier transformation, it is linear. So you can see there's a big discrepancy for large flip angles, but for low flip angles, the lines are very, very close to each other. That is a so-called low nutation angle approximation, and Fourier transformation works quite well in this region. So Fourier transformation has been used in pulse design, and still some of the pulses that we use today, like sinc and Gaussian, are still being were designed by Fourier transformation and are still being used. But clearly, looking at this profile, we need better methods, right? This is not really acceptable for state-of-the-art slice selection. Well, Felix Bloch, the inventor of NMR, basically already gave us the tools to come up with better RF pulses. In his first paper, Nuclear Induction, he already gave us the equations that are needed to quantitatively describe the NMR experiment. With his Bloch equations, you can calculate mx, my, and mz when you have an RF pulse or a frequency offset or relaxation. Now, you can also extend these equations to take into account diffusion or chemical exchange. We will not talk about those today. Those will be part of a future video. But we will talk about the three basic Bloch equations that were described by Felix Bloch himself. The first equation is shown here. It is a differential equation, and this may look scary to some of you, but you just have to know how to read an equation like this. So the first term basically tells you that the longitudinal magnetization mz changes over time t according to two effects. And so dmz dt basically just tells you how the magnetization mz changes over time. Now, it changes over time according to the first effect. And the first effect is basically rotation of magnetization along the y-axis by a B1 field along the x-axis. And that rotates towards the z-axis, changing mz. The other effect is appearance of magnetization because of T1 relaxation. Maybe the magnetization was initially inverted. It recovers back to plus mz by T1. So these are the two effects that lead to a change in mz over time. You can also write a similar equation for the change in mx over time. Also two effects. One effect is rotation of magnetization that is along the y-axis towards the x-axis by a frequency offset vector. And the other one is the disappearance of mx by T2 relaxation. Finally, you can also write an equation for the time dependence of the magnetization along the y-axis. There are actually three effects adding into that. The first one is rotation of magnetization that was initially along the z-axis towards the y-axis by a B1 along the x-axis. Rotation of magnetization along the x-axis to the y-axis by a frequency offset vector. And finally, the disappearance of my because of T2 relaxation. So, these are the three equations that quantitatively describe the effect of RF pulses, frequency offsets and relaxation on mx, y and z. Now, you can certainly simplify these equations under certain conditions. For example, let's say we have the condition where there is no magnetization in the xy plane and there is no B1 field. Many of these terms will disappear, and you actually can solve that analytically coming up with the equation that was in the very first video on nuclear induction and nuclear magnetization, describing the return of magnetization along the z-axis following any perturbation. Now, what we're interested in for today's lecture is can we come up with a way to calculate the RF pulse given a desired frequency profile? Well, the other way around, knowing the RF pulse and calculating the frequency profile, that is very easy. That is a so-called forward solution to these equations, and that is very easy to do. The other way around, where you have a desired frequency profile and you want to calculate the RF pulse that achieves that, is much more difficult. That is a so-called inverse solution. Fortunately, there are a number of algorithms that achieve this inverse solution. They are outside the scope of this video, but I can tell you that optimal control theory and the Shinard-LaRue algorithm are both highly successful algorithms to achieve just that. Just to show you the result of that, the red one is again the sinc function that was described and optimized by the Fourier transformation, and the green function is now optimized using the SLR algorithm. You can see it's a fairly minor deviation, but when we look at the frequency domain profile, it has big effects. Right? The sinc function has these undesirable wiggles outside slice and not a uniform inversion inside the slice. The green SLR optimized pulse now has effectively no inversion at all outside slice and a very nice homogeneous inversion inside the slice. So these are very successful algorithms to design a wide range of RF pulses. Now you can imagine that you can design dozens, if not hundreds, of different RF pulses with different bandwidths, with different transition widths, etc., etc. So we need a few tools to kind of quantitatively describe this large collection of potential RF pulses. So in the time domain, the important parameters will be the duration or the pulse length, and then the maximum amplitude that you need, B1 max, to achieve a certain flip angle. Another important one is the root mean square B1 or the average B1. This is important because that plays into RF power deposition and SAR calculations. Then in the frequency domain, important parameters are the bandwidth, the excitation bandwidth or the inversion bandwidth, the transition width, how fast goes the frequency profile from no excitation to full excitation. Then how large are the imperfections or the stop band ripple outside the excitation band, and how much are the imperfections inside the pass band or the pass band ripple. Now, on most MRI scanners, they have these parameters stored for the RF pulses that are available on the MR scanner. Typically, the bandwidth and the pulse length are a constant. And for today's video, we'll denote that as an R value, the R value of the bandwidth. The transition times the pulse length is also a constant for a given flip angle, and we'll denote that as R transition width. Then the equation from the very first slide of today's lecture determines the flip angle is 360 degrees times the B1 times the duration. Or for a shaped RF pulse, you need to incorporate the integral of the RF pulse times the duration times the maximum amplitude. Now these values are generally stored on the MR scanner in a table something like this, where you have a given RF pulse. For a given flip angle, you're going to have an R of the bandwidth and an R of the transition width. You're going to have an integral, you're going to have a root mean square integral, and there's going to be an F value, and I'll explain what that is later. I think for the remaining few minutes, I want to quickly go over some of the calculations that the system does for you using these values. So a very common question that you may have is, okay, I want to excite a bandwidth of 2 kHz and I want to use a sync pulse. How long does that sync pulse need to be to achieve this excitation bandwidth? Well, if you look into the table, you can see for the sync pulse, the R value is 5.95. The bandwidth that you want is 2 kHz, and therefore the pulse length is R divided by bandwidth is about 3 milliseconds. Then the next question that you can have is, what RF amplitude B1 max do I require to achieve this bandwidth with that pulse length? Well, the integral of this pulse is 17% of a square pulse. A square pulse is by definition 100% area, 100% integral, and therefore in this case the sync pulse is 70% of that area. The pulse length is about 3 milliseconds, the flip angle is 90 degrees, so the RF amplitude is given by this equation, ending up to be 473 Hz. You can convert that to microtesla by knowing that 100 microtesla is 1 Gauss, and 1 Gauss for protons is 4257 Hz. You want to be familiar with these kind of conversions because they happen all the time in NMR, where an RF amplitude is either expressed in Hertz or in microtesla or in Gauss. Knowing this, sometimes you want to know what is the amplifier setting in decibel that I need to achieve this amplitude. Well, the system typically does a calculation, a calibration for you. For example, it may calibrate using a 2.5 millisecond square pulse. And let's say that this pulse gives you your inversion at an amplifier setting of 10 decibel. What is then the power of the pulse that we want to use? Well, the square pulse, its RF amplitude for this duration corresponds to 200 Hz. Our RF amplifier, our RF pulse needs 473 Hz. So our amplitude needs to be 473 divided by 200 is about 2.4 times higher, which in decibel units using this equation corresponds to 7.5 dB. So we need to be 7.5 dB higher or lower than the calibrated 10 dB to achieve our 90 degree with our sync pulse. So these kind of calculations are done by the system for you, but I think it's good for you to understand the flow of these kind of calculations. Finally, if you go back to the table, the final column had an F value, and that is an important value as well. And I'll explain here what that means. So let's say that we have a Gaussian RF pulse that we want to use for slice selection. So we have a gradient underneath. At the beginning of the RF pulse, the magnetization is along the z-axis, and the B1 field is along the x-axis perpendicular to it. When you run through the pulse, the magnetization is being tipped away towards the xy plane. As soon as it is being tipped away, the mxy component is being dephased by the gradient. So spins at different spatial locations acquire a different phase. And at the end of the RF pulse, the magnetization has indeed been excited towards the xy plane, and all the magnetization is excited, but spins at different spatial locations have different phases. And if you would acquire the signal at this point in time, you would get very little signal because of the phase dispersal. Now, what you can typically do is you apply a negative gradient of a certain amplitude that then refocuses this phase dispersal so that all of the magnetization is again in phase and you get 100% signal. Now that f value is now defined as the area of this negative gradient divided by the area of the positive gradient. Now for a time symmetrical RF pulse like a Gaussian or a sync pulse, this f is always 50%. However, for time asymmetrical RF pulses, this f can be larger or smaller than 50%. But it is a convenient value that allows you to calculate what negative gradient do I need to apply to basically undo the phase dispersal across my slice. We'll talk about that more in future videos. So to wrap up, RF pulses are really at the heart of all modern NMR experiments, and you really need to understand RF pulses to design an optimal study. Frequency-selective RF pulses are pretty much the most commonly used, while a square or hard RF pulse is easy to understand. Its uses are limited in vivo NMR, because in vivo NMR you always want to, most of the time you want to select a spatial volume, either a slice or a volume, and so therefore you need frequency-selective RF pulses. Also, when you do water and lipid suppression, you need to have frequency-selective RF pulses that only affect the water or the lipids. And finally, for spectral editing, you also require these pulses. You can use the Fourier transformation to design these pulses, and sync and Gaussian are still being used. They're simple pulses, but they still work surprisingly well. But if you want to get better frequency profiles, you need to have dedicated algorithms in which you can define the band width and the transition width of these RF pulses. And the optimal control theory or the Chenal-Leroux algorithms are really well designed to deal with this. Here's a few of these calculations that I think you should be familiar with, even though the system will do most of these calculations for you. Finally, if you want to talk to me, if you see me at meetings, come and say hi. You can always email me, of course, and you can read a lot of details about RF pulses in the 3rd edition of this book. Finally, I have a piece of software called Pulse Wizard, which is a MATLAB-based graphical user interface in which you can design, you can generate, and you can simulate RF pulses. It is completely open source, and I'm very willing to share that with anyone who is willing to use that. So just shoot me an email, and I will send you a zip file containing this software. Thank you for your attention, and I hope to that you will watch future videos with me. Okay, bye.